Welcome to Part 19 of Applied Chemistry, focusing on Portland cement and glass. Portland cement is a type of hydraulic cement commonly used in concrete and mortar. It sets and hardens when mixed with water, creating a solid, durable mass. Because of its reliability and strength, Portland cement is one of the most widely used construction materials worldwide. This cement's unique properties are achieved through a precise manufacturing process involving high-temperature treatments. The manufacturing process of Portland cement involves several steps, with the rotary kiln being central to production. Raw material preparation. The primary ingredients are limestone and clay or shale, which are finely ground and blended into a mixture called raw meal. Heating in rotary kiln. The raw meal is fed into a large, rotating cylindrical furnace or rotary kiln, where temperatures reach 1,400 to 1,450 degrees Celsius. This high heat initiates complex chemical reactions, transforming the raw materials. In the rotary kiln, the raw materials undergo critical transformations. Calcination. Around 900 degrees Celsius, calcium carbonate decomposes into calcium oxide and carbon dioxide. Clinker formation. At higher temperatures, calcium oxide reacts with silica, alumina, and iron oxides to form clinker, a gray, nodular material. Cooling and grinding. After the clinker is formed, it is rapidly cooled and then ground into a fine powder. Gypsum is added during grinding to control the setting time of the cement. Gypsum is added during the grinding process to control the hardening rate of cement. Without gypsum, cement would set too quickly, limiting workability. By slowing down the setting time, gypsum ensures that construction professionals have adequate working time to shape and position the concrete or mortar as needed. When water is added to Portland cement, it initiates a series of chemical reactions known as hydration, forming a solid structure. Key compounds involved include tricalcium silicate, reacts with water to form calcium silicate hydrate and calcium hydroxide, providing early strength. Dicalcium silicate, hydrates more slowly, contributing to strength over time. Tricalcium aluminate and tetracalcium aluminoferrite react with water in the presence of gypsum, controlling the setting behavior. These reactions collectively give cement its characteristic strength and durability. Glass is an amorphous, non-crystalline solid primarily composed of silica. Its transparency, versatility, and resistance to environmental factors make it essential in various applications, including construction, packaging, and consumer goods. The manufacturing process and added ingredients determine glass's final properties, from simple window glass to specialized lab equipment. The tank furnace is the primary equipment in continuous glass production. Raw material preparation. Silica sand is the main ingredient, with soda ash to lower the melting point and limestone for durability. Additional oxides can modify color and properties. Melting. Raw materials are combined in the tank furnace and heated to around 1,500 degrees Celsius, melting into a homogeneous liquid. This molten glass is ready for shaping. Once molten, the glass is formed into various shapes. Forming. Techniques such as blowing, drawing, and rolling shape the molten glass into sheets, containers, or custom forms. Annealing. After forming, the glass is gradually cooled in an annealing oven. This controlled cooling process relieves internal stresses, enhancing the strength and durability of the final product. Annealing is a crucial step in glass manufacturing. By slowly cooling the glass, the annealing process reduces residual stresses that could otherwise lead to cracks or shattering. Proper annealing improves the stability, durability, and reliability of glass products, making them suitable for various applications, from windows to laboratory equipment. Different types of glass are made to meet specific requirements. Soft glass, made mostly from soda lime, it's low in melting point, easy to shape, and used for windows and bottles, though it's not highly resistant to temperature changes. Hard glass contains alumina, making it more resistant to thermal shock than soft glass. Used in laboratory equipment and cookware. Borosilicate glass contains silica and boron trioxide, which grants it high thermal and chemical stability. It's known for its resistance to temperature changes, making it ideal for lab equipment, optical lenses, and high-quality cookware. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.